Alrighty. Welcome back. So, I thought I'd just kind of start with the whole point of this chapter, or kind of stuff that we started talking about yesterday, which is really, a happy little rhyme here, or for something that's perhaps not so happy. The solution to pollution is dilution. So we're going to see that the more we can do to kind of lessen the concentration of things, the better we're going to be overall in terms of the environmental impact of things. So if we can lower the concentration, that equals good things. And so kind of yesterday we were talking about SOx, right, and acid rain. We talked about how coal burning, had a bunch of problems with low sulfur coal being more expensive and less efficient. And so, just to kind of illustrate one way that people have approached this problem is we can remove some SO2 from coal burning by precipitation. We're going to precipitate it out. And not like rain precipitation, but solid formation, KSP, that sort of precipitation. And so what happens is when you're burning the coal, the SO2 from that coal is put through a tank that has calcium oxide in it with lime, or slaked lime. And what happens with that is these two are allowed to react to form calcium sulfite, which would precipitate out of solution. And as a result, this can be collected. Wow, I can't spell already. Collected as a solid. And effectively, this will remove some of the SO2 from getting in the atmosphere. So it is diluting the amount of SO2 that would be released into the atmosphere after, through the exhaust of burning this coal. And so as a result, by capturing it as a solid, we're removing it. We're decreasing our concentration of SO2 in the exhaust air. Unfortunately, it doesn't get all of the sulfur dioxide out, but it gets quite a bit of it. And as a result, collecting it as a solid will lower the concentration in the air as a result, and thereby help to mitigate some of the bad things that SO2 can do in the air, namely the acid rain portion there. So that's one way to kind of fix this sort of thing. Of course, ideally producing less SO2 in the first place would be a better idea, but if nothing else, at least we can kind of mitigate after the fact. So bit by bit. Alrighty, so that's kind of the end about sulfur dioxides for now. Let's talk about smog. So, smog, as we may know, is a word that comes from the combination of smoke and fog. It is a portmanteau. That's our fancy vocab word for the day. But this kind of description is more accurate to one type of smog, which sometimes is called the London smog. If you picture 1800s or early 1900s London, it's always kind of this gray, kind of dreary place. So London typically gets quite a bit of fog. And at that time, people were burning coal in their fireplaces at home to keep warm. But what would happen is the smoke or the soot from the coal soot is the black stuff that stays after a fire. So, like, ash is another product of fire. That's the white stuff. Ash is typically salts, like potassium salts or sodium salts. But soot is carbon that's left over. Just kind of particles of carbon. Um, I guess I could write that. And when that forms with fog, it kind of holds it in stasis as a colloid. So that smoke ends up kind of staying there. So normally, smoke goes away, it billows out, and it goes up into the atmosphere and, will disperse and all that sort of jazz. But when fog is involved, it kind of traps the carbon particles at low altitude. So normally, if you think about, a smoke, goes up and off it goes and it's out of the way. However, with fog, if we have fog around here, the smoke ends up just going into that fog layer instead of just going out and about. And so as a result, since it's all trapped at low altitude, that concentrates it. Since we're just adding more and more smoke in there, and there's nowhere for that smoke to go, it stays there. And as a result, there were periods in London where they would have, heavy fog episodes for a couple of days, and people would actually just die from being outside, from breathing in all that soot. You've probably heard, in documentaries about coal miners with black lung. Just imagine that, but for everybody, just walking on the street would fill your lungs with soot, with carbon, with ash. All these sorts of bad things, and people would die, pretty frequently. And so this was unfortunately a common occurrence in, turn of the century London. And so this was a problem. So this type of smog, sometimes it's called London smog. And that's where that original word came from, the smog word. However, you probably also know that Los Angeles is known as pretty smoggy, right? But that type of smog, Los Angeles smog, wow, not London, Los Angeles smog. Yeah, so exactly. So you go, there's just these periods of bad weather where all of the soot and stuff would get trapped and just would kill people. And so it was incredibly unhealthy. And so, even in movies, you see old London as just this gray, horribly gloomy area for that reason. Los Angeles smog, though, is of a different variety. We typically don't get a lot of fog in LA, right? You don't typically see LA as cloudy. It's very sunny, right? Is what's called photochemical smog. And so this is actually just pollutants. So it's not going to be soot, like not actual smoke, but it's going to be various compounds that are being formed there that are hazardous. Typically, we're going to be looking at ozone and NOx. So ozone, as you've possibly seen on your weather app, if you looked at it yesterday, you'll see it again, that's the most common pollutant. Usually it'll tell you what the most common pollutant is that day. This is a big reason for photochemical smog. So we see that on those kind of muggy days where it's very sunny and hot out, and maybe there's some kind of haze in the air, that's photochemical smog. So it's different from London smog, which is kind of smoke, actual smoke, and fog mixing together and making that kind of layer that things can't get through. This kind of smog is chemical smog. So it's caused by light-based reaction. So as we know, Los Angeles is a very sunny place, not very foggy. And we're going to have various reactions that are going to be taking place. And so kind of a big one, I have the delta H for it here, is going to be 180.8 kilojoules. Let's say that's going to make nitric oxide. Pretty endothermic process, right? As we can see here, pretty high delta H value. Doesn't normally happen. We're going to see that in combustion engines, though, where a big of sort of this stuff will be produced, this is going to kind of be, at room temperature. The Kc for this is about, I have this here, 10 to the minus 15. But in a car engine, this rises to Kc of about 10 to the minus 2. As you can imagine, that's a very big difference, right? 10 to the 13th there. So we're going to see that we're going to end up producing a lot of this nitric oxide. So this happens, of course, it's much more common at high temperatures in your car engine. As we can see, it's endothermic, so the higher temperature you go, the more you're going to push that equilibrium to the right, forcing more nitric oxide to be formed. So as a result, you end up increasing your value of K, your equilibrium constant. So we end up producing this. And that in itself is not necessarily a bad thing. Nitric oxide, whatever, it's a hormone. Our bodies produce it. If you're having allergic reactions to things, you typically produce more nitric oxide. It just helps dilate your blood vessels. But we have problems. When this interacts with oxygen, we form NO2. Which has its own delta H here of negative 113.1 kilojoules. I guess I should balance this reaction. So perhaps doesn't seem terrible by itself, but as we go forward, this species then is photoreactive. And so there will be light of sufficient intensity to photodissociate this molecule into the nitric oxide again and an oxygen radical. This is in the presence of light. And unfortunately, when then we take the O2 molecule and add it to the molecular oxygen, we would get ozone, which is our problematic compound. Ozone is extremely toxic. Very, very potent oxidizing agent. It's pretty unstable, so it will react with a lot of different things. If you breathe it, it is a very bad thing to breathe. You do not want it. We want it in the stratosphere. We do not want it in the troposphere. We do not want to be breathing in ozone. And so ozone is actually going to be the big, big problem of pollution in urban areas when we have these conditions for smog. So if a lot of people are driving, we see a lot of nitric oxide being produced. That nitric oxide acts as a catalyst to produce oxygen radicals, which combine with dioxygen to make ozone. As we can see here, by the way, both the NO2 is an intermediate. Technically, the NO is also an intermediate here. I lied, it's not a catalyst. But these intermediates are necessary for this kind of process to take place. If we're just looking at this one, actually, it's acting as a catalyst. It depends if we're looking at the entire set of reactions or not to determine if it's a catalyst or not. But suffice to say, bad thing. When we produce NO, it can act as a catalyst, producing oxygen radicals. That's not a good thing because that can make ozone severely toxic to us. So, on days that are smoggy, it is recommended you go indoors. Ozone doesn't live very long. Ozone lives for about 100 seconds or so. Before it finds something to react with. That's just the typical lifetime of an ozone molecule. And so on smoggy days, where you have that kind of haze from the nitrogen dioxide there, um, it's a good idea to stay indoors or to at least close your windows, because by the time an ozone molecule gets in through the various vents in your house, it will have already broken down through that 100-second time frame. So, good idea to stay indoors on smoggy days. So this was a problem in the 70s. Lots of lung damage came out. However, at that point, the Clean Air Act was passed, which required cars to have catalytic converters to prevent that nitric oxide from forming. And so, as a result for that, we are producing quite a bit less smog than we used to through these catalytic converters. But it's still not, a perfect situation. We also will see that there are kind of incomplete combustion products. So we know combustion produces carbon dioxide and water, but sometimes if you have incomplete combustion, you get things like carbon monoxide, for example, that would come out of an engine. Again, greatly remedied by catalytic converters that help convert this into carbon dioxide, much less toxic. So if you see old movies, people would commit suicide by turning on their car engines in a closed garage, and the carbon monoxide would build up and kill them. But it's a bit harder to do that nowadays, just because our cars are producing quite a bit less of these incomplete combustion products. Don't do it, by the way. Please do not have your car running in a closed area. But suffice it to say that this is less of a problem than it was before. So, more kind of toxicants that are coming out of smoggy days. So, but things that have gotten better. So cool. Any questions on this kind of like air pollutant stuff? Let's see. I don't think there's anything else in our idea here. All right. Last thing for this section is greenhouse gases. And I'm going to kind of simplify this. This is the Earth. It's a very lovely drawing of the Earth. Sun rays come to Earth, yes. Heat up the surface of the Earth. Many get reflected back or are radiated out. However, these gases prevent heat from leaving. They can absorb the heat and re-emit it back down towards the Earth. And essentially what they do is they can prevent heat from leaving the atmosphere. And oddly enough, the most prevalent greenhouse gas is water. Water is our most prevalent greenhouse gas. There are many others. Carbon dioxide, methane, for example, are also very common ones. Also, our SOx and NOx are going to be greenhouse gases as well. Water is a particular greenhouse gas of note. Perhaps we see this in the most obvious case in deserts, like ridgecrest. For example, we know that ridgecrest is very dry. We do not have a lot of water in the air here. And as a result, it gets very hot during the day and very cold at night because we don't have this greenhouse gas trapping heat here. In contrast, if you go to coastal cities, if you go down to San Diego or something, or Malibu or Santa Barbara, those places have a much narrow temperature range for their day and night kind of transitions. Santa Barbara may go from 70 during the day to 60 at night, and that's it. Whereas in Ridgecrest, we might go from 80 to 30 in one night, simply because there's a lot more water in the air in the coastal areas. They're next to bodies of water. There's a lot of evaporation happening there. And so that water traps heat in the atmosphere. And we're going to see that all these other greenhouse gases contribute the same way. So they overall kind of force heat back into the atmosphere instead of radiating out into space. Methane is probably the second worst one. All of these gases are, they all kind of have their own, heat capacities and that sort of thing. Methane's is a pretty large one compared to carbon dioxide. So carbon dioxide is bad enough, right? But methane is even worse. And so methane is produced, as we know, by cows or fracking or various industrial things. And so released into the atmosphere that way, and sad things happen. Sometimes, though, you'll see that some places have continuously burning fires. Interesting, there's this place, I think in Russia, or somewhere out there, that's been on fire for about 50 years or so. It's just a hole in the ground that's on fire because of methane and other gases in there that are burning. And that fire is intentional, and they're keeping it on fire because the combustion of that gas produces carbon dioxide, which is much better for our atmosphere than methane is. So sometimes it's intentional if there are gas leaks or whatever, that you intentionally burn them to prevent the methane from getting out, because methane is worse. So, just more kind of real life stuff you'll see. I'll see if I can find the article on it. It's pretty interesting to see this hole in the ground that's just on fire, a portal to hell, as it were. So, pretty cool stuff. All right, but you've probably heard about greenhouse gases all your life, so let's move on to water. So, water. I guess we should start with the water cycle. Enough about atmospheric problems and gases. Let's talk about water contaminants. Let's see. There are much kind of better examples of diagrams of this than I can draw, but suffice it to say, water kind of moves around the planet in many ways. We kind of have, let's see. Let's draw some water there. And then we have land. And here's a tree. There it is. It's a Christmas tree. And here's this mountain. And here's a rain cloud. Okay, cool. Okay. Suffice it to say that water is moving all around these all of the time. Here's an ocean, by the way. We know that water is evaporating all the time. We know that water also precipitates as rain and snow. Either that is going onto land as rain, or onto higher elevation areas as snow, or colder areas. Plants give it off through a process called transpiration. There's also evaporation that happens here. We also have evaporation from land, of course. We have snow on these mountains. That comes from precipitation. That can either come off as water through just melting, or it can go underwater as groundwater, which eventually can get flushed into the ocean as well. And so these could be like streams and stuff, streams and rivers and lakes and all that good stuff. They flow out. Eventually they'll reach the ocean as well. But, they're kind of all in this process of evaporating and precipitating and all that all the time. So water is constantly like moving around the planet the whole, all the time. So through a bunch of different processes. And we're going to talk about kind of individual sections of all of these. So just for some numbers, I think the number is here somewhere. It's pretty interesting to see. The oceans have about 97% of the world's water supply is in the ocean. All of the water in the world is in the ocean. We have 2.1% as snow or ice in polar areas or mountains. So as you can see here, we have 0.7 left percent of the water. And we're going to see about 0.6% is in streams and groundwater. And then the last 0.1% are in non-ocean salt water. So, interestingly enough, of all the water on the planet, really 0.6% of it is accessible to us as fresh water. And so, some of the groundwater is not accessible to us at all. It's completely underground, we can't get to it. But just to kind of show you the magnitude of where, water happens to be at a given time. This is kind of what we're looking at here. So, I guess first we should talk about ocean water, right? Being the most kind of common water body. The ocean, believe it or not, is pretty constant in composition across the world. The ocean is, what we say on geography is, we have the Pacific Ocean and the Indian Ocean and Arctic Ocean, whatever. They're all the same ocean. There's kind of just arbitrary boundaries in between them, but they all connect to each other, right? The continents are all waterlocked, or water-bound. Landlocked? No, waterlocked, I guess. Anyways, ocean has pretty constant composition, no matter where you are in the world. And often we describe what's in the ocean using a term called salinity, which is the grams of salts per kilogram of water. That's pretty similar to parts per thousand. So sometimes we talk about things as parts per million, parts per billion. But salinity is a term that we talk about with the ocean, and it is parts per thousand. So grams of salt per kilogram of water. And so the ocean has a salinity of about, I think, 50 or so. I have this here somewhere. Who cares? We don't need the whole thing. But let's have a look at some of the kind of common ions in here. So from your book, I have a table. We have various ions here. We've got magnesium in there, calcium. I don't know, what else do we have? Potassium, CO2, bromide. Who cares about the rest? Good enough. We're going to see that the salinity of these, or the parts per thousand grams per kilogram, we're looking at 19.35, 10.76, 2.71, 1.29. I really just want to get through bromide because that's an important one. 412. Again, these numbers you do not need to know by any means, but they will be interesting to talk about. And bromide, where are you? 0.067, okay. Because bromine is actually one of the important salts we get out of the ocean, or bromide rather. So we can see here some of the more common ions that are present in seawater. And so we see that the biggest one is chloride, of course, balanced out by a bunch of positive things in there. A couple of important things to talk about. Are these four. We can talk about carbon dioxide first. Carbon dioxide is often going to be as the bicarbonate and carbonate forms, which we have learned last chapter that these can form a buffer, right? And these will help to buffer the ocean. I think it's about 8.3 to 8.5 or so is where the ocean's pH tends to lie. However, as we know, carbon dioxide is an acid. When you combine it with water, it forms carbonic acid. The more carbon dioxide that is absorbed by the ocean, the larger concentration of carbonic acid you have, which will eventually lower the pH. So we have problems of ocean acidification as well, where calcium carbonate-based things like corals and shells of various animals are breaking down more easily than they should because of more acidic conditions in spots in the ocean. But that's another problem. So, bad things. So that's something people are trying to solve. Again, carbon dioxide is kind of just this like horrible molecule for the environment, right? Traps heat in the atmosphere, and also acidifies the ocean. So, and inadvertently heats up the ocean because heat transferred in the trapped in the atmosphere ends up in the oceans anyway. So, that's enough about carbon dioxide. You're probably sick of it right now. But the ocean is our biggest or most consistent source of sodium, magnesium, and bromide ions. And these are all very important to us, both kind of as chemical reagents, of course, but also for life, right? Salt is something that our bodies depend on. We need a lot of sodium per day because we sweat a lot. That releases the sodium from our bodies. And so that's our biggest cooling mechanism. We also put salt out in our urine. And so we always are replenishing it. Back in the day, salt used to be a very expensive commodity. And so, people would, spend a fortune on salt, just getting it from people who live near the ocean. Salt does happen in mines as well. There are salt mines and that sort of thing. And, there are places that have more other mineral heavy salts like the Himalayan pink salt or Hawaiian black salt or stuff like that. Magnesium is an important kind of component in chemical reactions industrially, but it's also very important in fertilizers. Chlorophyll will not work without magnesium, so if soil is magnesium deficient, plants die. So magnesium is kind of an very important bit there. And bromide is kind of useful that's more of a chemical industry sort of thing. Bromine is a very, very important chemical. When you take organic chemistry, you'll see that we use bromine quite a bit in organic chemistry. It's a very useful atom to incorporate into organic molecules. And so we use it kind of industrially. So we get a lot of this through a process called desalinization. Which will be basically either distilling or reverse osmosis to separate the water from these ions. Distilling, of course, is when you just boil the water, it leaves behind the salts. That's the end of it, and you can isolate it. But this is pretty energy intense. It's pretty inefficient to be boiling all this water just to isolate it. Of course, this can be coupled with pushing turbines and that sort of thing to make some electricity, but it's still pretty intense because you have to put in something to heat up that water. Reverse osmosis is a little bit less energy intense, but it's got more of kind of an upfront cost associated with it. With reverse osmosis, we use high pressure to force water across membranes, leaving salts behind. So normally osmosis, as we talked about, is water going from an area of low concentration to high concentration. Reverse osmosis is the opposite process. So we talked about osmotic pressure, right? That's the pressure of the water that wants to move. So if you apply more than the osmotic pressure, you get the water to move the opposite direction. And so you can force water to go towards a lower and lower concentration of salts, thereby purifying the water. And so, of course, having the equipment to make this high pressure, as well as the membranes, which eventually do need replacing every so often, it can be fairly costly as well. But it's more efficient than distillation is. I have a reverse osmosis thing myself on my sink because I hate the taste of the water here in Ridgecrest, and so I use reverse osmosis to make it so it doesn't taste very bad. Of course, you can filter the water as well. There are ways to remove salts through filtration, but it is typically less efficient than reverse osmosis is. Just so you know, reverse osmosis typically takes about 2 gallons of seawater to make 1 gallon of fresh water. So, it's not exactly a, 1-to-1 process here. It's in fact a 2-to-1 process. So you end up having a lot of wastewater that has to go back into the ocean or wherever you're getting your water from. This can also be done with what are called brackish water supplies, like Salt Lake City. The Salt Lake there in Utah is salty water, or the Dead Sea. These are saltwater areas that are not part of the oceans. You can use desalinization there as well. So, any questions so far, by the way? Or those were going pretty quick here, but that's okay. Alrighty. So typically, when we see that once we have kind of isolated the water, we call water with a salinity of less than 0.5 fresh water. So that means there's less than half a gram of dissolved salts per kilogram of water. We call that fresh water. And so fresh water is kind of the stuff that we'll have in our streams and lakes, and groundwater as well. It's the stuff we drink, the stuff we use to do our laundry, to shower in, to boil our pasta. We use fresh water for it. Well, I guess sometimes we use salt water for boiling pasta if you add salt to it. But anyways, again, this sort of fresh water is about 0.6% of the total natural water on Earth, right? So we don't have that much fresh water, but it is constantly being renewed. So we have evaporation that takes place, which is natural distillation, right? water turning into a gas, leaving the salts behind. It precipitates somewhere else as rain. We can collect that rain, and poof, now we have some fresh water. Or we go to a stream or river, and we can kind of, decontaminate it and have it as fresh water. Or we can get it from the ground. So we're going to see that of this, most of it, about 80% of this 0.6, is in streams and lakes and that sort of thing. However, about 20% of this is groundwater. So that is water that is trapped in rocks beneath the ground. So that water is trapped in porous rocks underground. And so that water kind of just stays there. It can be there for millennia. Thousands of years, that water is just stuck there. We can get to it. We can tap what are called aquifers. We can well what are called aquifers, which are kind of just regions of groundwater. And so, if you have a well or whatever, you're drawing water from the ground. You're drawing groundwater up. And so that's water that's trapped underground. It gets there just kind of as water goes through. It finds these kind of happy areas where it can settle into the rocks and kind of just sits there. However, as it sits there, depending on nearby minerals in groundwater rocks, things can leach in. Leach with an A. For example, hydrogen arsenate. So arsenic is an element, right? It's found in various minerals. If your groundwater happens to have minerals with arsenic in it, it can dissolve in that water. It can leach in, forming various arsenates, which of course are toxic. So sometimes we have to filter groundwater. Groundwater, is typically free of bacteria, but sometimes there may be toxic minerals in there. And so in Ridgecrest, interestingly enough, if any of you are paying a water bill yourself, you'll see that we're charged an arsenic charge, which is often the majority of the bill. But we have to do a lot of special things to get rid of the arsenic that's in our groundwater here. And so if we didn't, it would be unsafe to drink. And apparently in Bangladesh, there's an aquifer there that is so heavily contaminated with arsenic just from nearby minerals that drinking the water itself is poisonous. So for us, here in Ridgecrest, it's not, the arsenic is not necessarily at levels that it's going to kill us immediately, outright, but eventually over time, it's not a good thing to have. It takes a very long time to leave your body. So we do a lot of treatment to get rid of the arsenic here. And therefore we pay more. Hooray. Alrighty. Any questions? So, salinity, groundwater, ocean water, anything like that. Your homework is up, by the way, so you can kind of see the types of questions that you're going to have. So a lot of these are kind of dealing with salinity or this kind of more conceptual questions about water and that sort of thing. So I'm sure some may come up. Okay, anyways, let's talk about how humans mess up water. So, yesterday we had a section where we talked about humans messing up the air. Today we get to talk about how we mess up the water. Hooray! So, of course, dumping things into freshwater supplies is not a good thing. But we're going to see we have kind of a couple of vocab words to learn here. One of which is called eutrophication. And this is what happens when we dump or we have runoff of fertilizers or waste that contains phosphorus and nitrogen. Nitrogen is a very important component of fertilizers. It's very important for plants, but when that runs off, as in rain comes and washes some of that nitrogen or those nitrogen-containing compounds into ponds and lakes, they can go through a process called eutrophication. So, bacteria and plants, aquatic plants, thrive with extra phosphorus or nitrogen. Both of them typically. However, there's a problem with this. These need oxygen to survive. And what happens is if you continuously have extra sources of phosphorus and nitrogen going into, say, a pond, eventually those bacteria are so happy to see that extra phosphorus and nitrogen, they go into kind of overproduction. They replicate, they start kind of growing and growing and growing, and eventually they're going to end up consuming more oxygen than is available to them, and they end up dying. And so as a result, just so for your information, so oxygen in fresh water is about 9 parts per million of dissolved oxygen gas. Most things, bacteria, fish, or plants, need minimum of 5 parts per million of dissolved oxygen in order to kind of breathe, right? And so what happens is if you dump these nitrogen-containing compounds or phosphorus-containing compounds in, the bacteria are like, oh my goodness, feast time. The plants do the same thing. You end up consuming all of the oxygen while building yourself up, right? So when you're creating energy from glucose and all that, you need oxygen, right? And you need that energy to build yourself up, to grow, to cell, mitosis and all that sort of thing. And so, with extreme growth, we deplete the dissolved oxygen in the water, especially if that water is still. It's not moving. If it's not moving, we just have to wait for oxygen to diffuse into that body of water, which is an extremely slow process. If that water were moving, like with the ocean where we have crashing waves and that sort of thing, that helps dissolve oxygen in it because it forces oxygen in. But if it's just a flat water, oxygen has to actually come to the surface and be lucky enough to actually penetrate in and then migrate down in there. So it's not an ideal situation here. Once the oxygen is depleted, we have anaerobic processes take over. If you have oxygen around, the products of growing and dividing and metabolism are things like carbon dioxide, sulfur dioxide, nitrogen dioxide. Pretty common byproducts of oxygen-rich metabolism. However, when we deplete our oxygen, we end up making things like this. And so, hydrogen sulfide, of course, is your rotten egg smell. And ammonia kind of has that like kind of fishy smell. And pretty pungent. So if you've ever been to a pond or lake, and it kind of has this stink to it, and you probably see a lot of like really green algae on the top, those are lakes or rivers or ponds or whatever that have gone eutrophic. So they've gotten so much growth there. Trophism is growth. Eu meaning like good or strong. So there's so much growth going on in there that eventually all the oxygen is depleted, and so you only have anaerobic things that happen after, which produce these stinky things. And of course, all the fish end up dying as well because the fish need oxygen to survive, and if there's no oxygen, the fish die. And again, then you have more rotting and stuff happening, which again contributes to the smell and all that sort of gross stuff. So all your gross ponds and lakes are a result of eutrophism for having too much nitrogen or phosphorus present as a result of human interference. So that this whole chapter is basically humans suck. And that's what it is. So just write that on your exam, you'll get full credit. Pretty much fun stuff. So this is all a pretty depressing chapter, honestly. But anyways, let's see. Let's talk about water purification. How do we get pure water back? So, we've seen our freshwater supply is quite limited, 0.6% of the Earth's water. So, it's kind of in our best interest to purify what we have because we have a limited supply of it. And so, evaporation and all that takes a lot of time. So, we'll end up treating a lot of our wastewater to recycle it as fresh water. So, water treatment has a number of steps associated with it, where first water is placed into it does kind of allow the water to sit. If you allow the water to sit, that will break any suspensions. So large particles will form sediment. And they'll form sediment. So we know that if you just, if you take some sanded water, you shake it up, you let it sit, eventually all that sand will filter out and it'll end up at the bottom. And that's kind of what we're looking at here, is we just allow that water to sit there for a period of time, and the big stuff just filters out to the bottom where we can collect it and get rid of it. After that, we'll typically combine it with two compounds, calcium oxide, the lime, and some aluminum sulfate. Pretty common treatment materials here. The calcium oxide helps to make the water slightly basic, which just helps helps the aluminum sulfate to form aluminum hydroxide. And so by doing this, what's interesting about this aluminum hydroxide, we saw that it can form a complex at high hydroxide concentrations, but if it's just slightly basic, it's a solid. It precipitates out. But the type of precipitate this forms is very goopy. It's kind of gelatinous. So it kind of forms this jelly. And eventually, it settles down. It settles to the bottom and drags any other dissolved particles. And so, we'll just let the big particles filter out by themselves, and we'll push it through a sand filter as well. That'll usually get through most big particles. Then we add this mixture of calcium oxide and aluminum sulfate to form aluminum hydroxide, which is gooey, and it settles out very slowly, and as it does, it pulls down all the extra crap with it. Kind of a, dare I say, more gross analogy is that's how fiber works in our bodies. It forms this kind of gooey substance that helps to clear out our intestines. So it's the exact kind of same process here, is we form this kind of gel which helps to push things out. So it gets rid of all these kind of fine particles as we go through it. Afterwards, we'll add a disinfectant. So typically that's chlorine or ozone. Chlorine is kind of the best choice. Well, no, it's actually the worst choice. Never mind. And then we just kind of... actually, we sometimes will aerate it as well. That can happen before or after. Let's put that as 2.5. If we aerate it, just kind of allow it to, kind of put it through a fountain. If we aerate this, we'll remove volatile organic compounds. So if you have any volatile organic compounds in your water, you can aerate it to get rid of them. And then our last step is to add a disinfectant to kill any bacteria that may be, or parasites that may be present in the water. But we're going to see that there are problems associated with these disinfectants. And I guess we'll talk about those tomorrow. So, our nice despair chapter here. We'll continue. We'll actually finish off tomorrow. There's only one more section after this, which talks about green chemistry, which is pretty quick. It just kind of is a set of kind of like guidelines that we try to use to make our chemistry better for the environment. And after that, we'll be done with the chapter. So Thursday, we can have our review session for your exam on Monday. So yeah, I'll see you all tomorrow then. Enjoy your Tuesday. Your homework is up if you want to get started on it. Don't forget, both homeworks will be due this weekend. So both the one from Acid Base. Ooh, maybe I didn't put it on the honors one. Okay, I'll double check that right now. And then otherwise, I'll be good. Alrighty, I'll look at that and I'll post it in Discord. So, okay, see you guys tomorrow.